So it's my pleasure to introduce my collaborator, Dr. Joyce Wong, who's a professor in biomedical engineering and also in material science engineering here at Boston University. She works on tissue engineering and organoid culture, et cetera, and she's going to introduce our joint student. So welcome, Joyce.
Thanks, Kathy. So good morning, everyone. It's my distinct pleasure to introduce, as Kathy mentioned, our joint student, Isabella Claure. So she's going to talk to you about some work that we hope that will be of interest to you, because some of you may be interested in mechanobiology. And she's going to talk to you about an assay that with the DAMP lab she's been developing, looking at hydrogels. So welcome, Isabella.
Thank you, Joyce. Hi, everyone. So today I'll be talking about our pilot project with the DAMP lab looking at hydrogel preparation in a high throughput manner. So this was kind of exciting because it was the first time DAMP lab was going into the biomaterial space. And so I hope I'm able to highlight some of the challenges and being able to adapt the method to this completely new approach. So this work did stem from my own research, but it has broader applications. So within the field, there's a big interest in being able to recapitulate a cell's microenvironment. So as this figure highlights here, this is years and years of research, but we now have a better understanding that a cell's environment affects its fate and function. So some key examples of that are cell spreading, cell proliferation, but then also known examples such as stem cell differentiation, wound healing processes, and also tumor onset and tumor metastasis. And so because of this, we really want to be able to recapitulate that environment both in healthy and disease states, and then be able to understand cell behavior and apply that to new tissue engineering approaches and also drug screening platforms. So one of the more popular, maybe legacy materials in this space are polyacrylamide hydrogels. In this work particularly, they're of interest because of their tunable mechanical properties. So as the figure on the right highlights, as you increase the cross-linking density of these hydrogels, then you can increase the relative stiffness of this. And this covers the broad range of elastic moduli that are replicative of soft tissue. And so the downside of this, unfortunately, is that they're typically made in low batches, which is a relatively low throughput method. And if we want to be able to do this kind of screening work that we are interested in, we need to transition out of that. And so what our group was able to do is have this new approach that directly casts these polyacrylamide hydrogels in multi-well plates. And it's able to still utilize commercially accessible and low-cost reagents, which is very nice, and also it's a rapid and straightforward procedure that just requires liquids throughout the entirety of the process. And so part of why we want to scale up this synthesis process is it's an enabling step. So if we want to be able to do high screening, we need high throughput techniques. And what this enables us to do is doing analysis of stiffness-dependent cell behavior, physiologically relevant cell culturing, and also being able to now look at drug screening in the context of stiffness-dependent effects. But some of the challenges of making this in the lab are in regards to quality control and in-plate variability. So you can imagine it's a time-sensitive procedure. Once you start the polymerization, it runs on its own, and all the work needs to be done relatively quickly. And as you're pipetting through a 96-roll plate, user errors are common. So pipetting errors, handling errors, and the more plates you do, the more this error is magnified as well. And so partnering with the DAMP lab was an opportunity to use their expertise in order to have more reproducible and high quality plates and improve the efficiency of this production process. So before I go into exactly what part of the method they were automating, I kind of want to walk you through that to give you some context. So we start with these pre-treated plates that are now UV reactive, and then we introduce this polyacrylamide hydrogel solution. And what I have highlighted here in this figure is the modularity of the approach, where we can introduce different kinds of polyacrylamide hydrogel. So a low stiffness, medium stiffness, high stiffness, cast that into the plate, overlay this chemical to butanol, and then transfer it to UV exposure. Now, specifically what the DAMP lab focused on in this first attempt was to automate the hydrogel dispensing and the overlay of the 2-butanol solution. And our goal in this was to be able to have robust and reproducible hydrogel synthesis, covering the full range of soft to stiff hydrogels, and then also having higher quality and uniformity across the plate. So in our first goal, hydrogel quality. So we wanted these nice, smooth adhered hydrogels that you can see on the left, not these buckled hydrogels on the right, where you can imagine the cells would not be very happy on that. Topography will also affect cell function. So our goal was really those on the left. And there were two aspects to be able to accomplish this. So the first was in the initial handling and spread of the polyacrylamide solution. So we use the touch-off dispense for small volumes. These are 50 microliter solutions per well. And also this feature of the Hamilton to shake the liquid after it's dispensed and have even distribution. So this is even across the board. And it enables for these nice hydrogels where it's fully covering the surface of the well. Then we have the overlay of the 2-butanol. This is this on-the-fly dispense that should be popping up here. And so the key part of this was to be able to not disturb the liquid that we had just added to the plate. So we wanted to softly dispense the liquid and make sure it's evenly covering the plate as well. And so it's just highlighting here. I think it's very nice. It's a soothing video. But yeah. And then the next aspect of the work was now the modularity. So it's great if we can do one stiffness, but really what we want is to cover the full range of stiffnesses that we're interested in. So as you look at here, this ratio of the acrylamide to bisacrylamide is what tunes that stiffness. But as we go to a higher stiffness hydrogel, we're increasing the content of both of those. And what that does is affect the polymerization rate. So those gels are going to polymerize much faster than these softer gels. And if we want to be able to include both in the plate, we need a relatively fast process in order to do so. And inherent to the protocol itself, as that polymerization is happening, we need UV exposure as well to make sure that they're adhered to the plate. So all in all, what we needed was a fast method that ensures uniformity and modularity of the approach. So the key adaptations that they made to be able to do this is one in just the deck layout. So as you can see here, in optimizing this, the goal was that as you mount the pre-treated plate, as you move to the next step of shaking, dispensing the polyacrylamide, dispensing the butanol, the time between those steps is shortened as much as possible. And then as we're in those steps, that's as fast as possible as well. And what enabled the modularity of the approach is being able to do this parallel dispensing of the solution. So you can see in these plates that they were able to make, we have both single stiffness, dual stiffness, and triple stiffness across the plate with a sufficient N that we were looking for. So just to kind of summarize the services that we utilized, so we had the liquid handler set up, the addition of the polyacrylamide solution, and the addition of the 2-butanol overlay as well. Now for the exciting part, how efficient was this process? So if we look at just one plate, the Hamilton is about like 7 minutes faster. I think that ended up being the final number. But where you really see the benefit is in 4 plates and more. So as you add more plates, you compound that effect. So if we look at the manual to the automated, both total and hands-on time, the Hamilton is much faster at making these plates, and it has better efficiencies in regards to uniformity, the complexity of the plate that we're able to do, speed, and minimal user error. But really what these all kind of compound onto are the time-saving benefits. So the Hamilton is able to do these and make much better hydrogels than I am, and it's able to redirect my labor from being able to make these plates to now not only the downstream process of these plates, but also being able to do other projects and finish my thesis, all of that. And what's nice is this really is an on-demand research tool where not only can I pass on my project to someone else and they can pick up something that's the most replicative protocol that there is, but then also for other researchers as well. They can pick this up and do something and it's standardized across the board. So overall, we were able to successfully scale up this synthesis procedure, and it was reproducible, modular, and a greater efficiency in both time and labor. Now, some of the challenges that we faced in the scale-up are obviously in working with small and large volumes, things are very different, but then also in being able to recreate laboratory conditions across the board. So equipment is different. The Hamilton is not fully built to have the same equipment that a lab does, and then also specifically an example is the chemical fume hood. So this process does require some harsh chemicals, and not all of them were able to be used with the Hamilton. And so being able to look at maybe investing in expanding the capabilities in order to do the whole process from start to finish. But the biggest lesson we learned is in transitioning from a manual to an automated method, we want to go stepwise. So in understanding the procedure, we can go step by step and transition into the more automated method. And overall, the applications of this work, there are direct applications for my own research, but then there are broader applications for those interested, not only in mechanobiology, but I think more outside of that, if we look at developing more into the polymer synthesis realm. So with the damp lab, within my own work, we're looking at incorporating the UV exposure step, which was the last step of that procedure in order to reduce the hands-on time. And I think broadly, we can also expand our capabilities and apply this method not only to synthetic and natural hydrogels, but also in intersecting that with also 3D cell culture. And really, there's a big realm of possibilities for this work. So I want to thank everyone from the Wong and Clapperich labs and from the DAMP lab, Kristen especially. She was the one hands-on and did a majority of this work. So thank you for your time and any questions.
Question I have, so if you pass along like the DAMP lab and make plates,
Yes.
how long are those plates good for? Like, do you have
Yes.
to use them immediately or can you store them?
So typically the literature varies, but you can store them. I think they recommend using them within about a week or so to ensure that it is the same stiffness as when you made it. But yeah, there is an off-the-shelf aspect of this, which is nice. Yes.
Oh, hey, talk more about the.
Oh, no, go ahead.
Can you talk more about the 3D cell work that is envisioning that do? Is it with the hydrogel too, or are they just separate?
So this would be separately. So with these hydrogels specifically, you can't seed cells during polymerization, but like a great example are collagen hydrogels. So as those are polymerizing, you can encapsulate cells and then you have this nice 3D matrix. And I think there are many people on campus that do more complex work than that could be amenable to this process.
We have our visibility from you actually.
Yes, so that is a great question. So we have some preliminary work that does validate the stiffness of this, the stiffness of the hydrogels with the method, and it is similar to what we're expecting. And we are in the process of validating in the multi-well format. So we have equipment on campus that works for 24 well plates, but not 96 well plates. So we're talking with the company to use their new instrument to be able to validate in the 96 well format. So it's from Optics 11 and it's the Pavone nano indenter. That's the 96 well. We have the Puma.
So that implies that it's an optical method. Like I'm wondering what physically.
So those instruments work. It's similar to AFM. So it's doing a nano indentation method.
An indentation.
Yes. Yeah. So it has a cantilever.
So it's a hardness. Very soft.
Yes. Yes, exactly.